Welcome everyone, and welcome to the AluVET Vocational Training and Education for the Aluminium Sector. This training is co-funded by the Erasmus Programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metal series of modules explains the theory of metals and of metallurgy to enable students in subsequent modules to understand aluminium, its alloys, heat treatment, and how it is rolled, extruded, and or welded. This project is funded with the support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. The aim of this module is to provide knowledge about how metals solidify into cast macrostructures, to understand the metallurgy of cast structures, to understand the nature of cast structures, their chemistry and properties, so the limitations of castings. In this module, you will understand how cast structures form on solidification, about the macrostructure and the chemical segregation that forms within cast structures. You will appreciate the need for correct homogenization heat treatment prior to wrought working. You will understand how flaws and defects can form within cast structures, and so you will appreciate the limitations of cast structures. In the preceding modules on solidification and on grain size and alloying, we learned how liquid aluminium solidifies on an atom-to-atom scale to form alloys and grains. Cast structures are not homogeneous. They change from surface to core. Both their structure and chemical analysis can vary, and they can be heavily segregated. Thus, cast structures can exhibit variable mechanical properties. In this module, we shall understand how the structures we actually see form on solidification and understand the nature of those cast structures. This module will explain why we need to apply homogenization heat treatment to cast aluminium before subjecting it to wrought working, such as rolling or extrusion. Now, fusion welds are miniature castings, so it is important to understand what structures they can form within the weldments. So let's understand casting and the process. In casting, we're going to pour liquid metal into a mold. And the mold might be sand or steel or ceramic. The mold walls are very cold in comparison to the molten aluminium. The liquid aluminium temperatures can exceed 550 degrees Celsius. So when we pour molten aluminium into a mold, As soon as the aluminium touches the mold walls, the aluminium in contact with those mold walls will instantly solidify, forming small chill crystals. So as soon as the aluminium touches the wall, it's a solid and it's formed chill crystals. The aluminium solidification starts from the cold mold walls. So nucleate solidification, forming the face-centered cubes, then the lattice, and now chill grains. The chill grains line the mold wall, so they change the cooling rate. Because they line the mold walls, all of the mold, they slow down cooling. They act as a barrier. The chill crystals have now formed a complete barrier around the mold walls. They have now slowed cooling. The cooling slows, so the next grains to form are long columnar grains. Because the cooling slowed, the solidification rate has slowed down. So now long columnar grains start to grow inwards from the mold walls to the center of the casting, perpendicularly away from the mold walls. We've slowed the cooling rate down. Now cooling is slower, so we're now growing long grains inwards from the mold walls. These columnar grains grow like fir trees from the mold walls. Like fir trees, they grow horizontal branches with spines that almost resemble pine-like needles. Now, the solidification during casting is too rapid for equilibrium to be maintained. By that, I mean, as the liquid cools, the chemistry changes from the walls inwards because the cooling rate is so fast. So the columnar grains grow dendrites. Dendrites are these fingers with spines rich in segregated alloys as they grow. So as they grow, their chemical analysis changes. Because we're cooling so fast, the chemistry of the liquid metal cannot be maintained. So as the grains grow and they grow inwards, their chemistry changes both longitudinally and in the branches and the spines. Hence, these columnar grains are anisotropic. That means they have directional properties because their chemistry and their mechanical properties vary with growth and the cooling rate. Let's look at the chemistry. Now, as the mold wall solidification starts with atoms forming a single cube, the nucleation grows into chill crystals. Now, the analysis of these chill crystals, if you remember in previous modules, will follow the solidus line. So the analysis of the chill crystals will change from the solidifying liquid to that of the solidus line, following that of the solidus solvent chemistry on the horizontal line. Now, as cooling continues and the columnar fir trees grow, the colder metal that solidifies will follow the solidus line. If you remember in the previous module, as the liquid cools, it drops down and it goes horizontally onto the solidus line, and the chemistry moves towards the solute. So the analysis of the fir trees will change from the chill crystals, and as the fir trees grow inwards and their cooling rate slows down, their analysis will change following the solidus line. They will become more richer in solute atoms. Now that means that the columnar grains exhibit a core inner and outer chemistry. So the columnar grain chemistry changes from the mold wall into the mold and into the branches. Now, as we solidify, the solute atoms and inclusions are pushed by the columnar fir tree solidification front into the center of the castings. As the columnar grains grow, they insulate the liquid metal from the cold mold walls, so the cooling rate slows down more. Consequently, in the center of the casting, the cooling rate is very, very slow, and the cooling now occurs from all directions. The columnar cooling rate is from the mold walls, but as in the core, we've got cooling coming from all directions of the mold wall, from all the liquid. So we now form equiax spherical crystals. Because these crystals are spherical, because in the center of the casting, cooling is from all directions, no longer driven from the mold wall. So in the center of the castings, we form equiax semi-spherical crystals. These equiax crystals have isotropic properties. That means that they are identical and homogeneous. And equiax crystals are therefore very, very desirable, as they have a homogeneous structure, homogeneous chemistry, homogeneous mechanical properties. And for that reason, we can promote equiax crystal growth by using low pouring temperatures or inoculants into the castings. Now, finally, as the remaining liquid metal solidifies, shrinkage occurs. Remember, the casting was fed from the walls outwards. We had chill crystals, columnar grains, and now equiax crystal. And right in the middle, we've got final solidification metal. So as it solidifies, it can't be fed. There's no more further molten metal. So some shrinkage will occur in the center of the castings. So let's now give an overview of casting microstructures. So during casting, all metals will develop 3 different macrostructures. The macrostructures will all form at different cooling rates. The different cooling rates cause segregation of alloys and chemical analysis during the castings. So castings are heterogeneous. They have variable analysis. Castings are heterogeneous, so they have mechanical variable properties. And castings are prone to shrinkage and porosity. Now remember, fusion welds, particularly those fusion welds where we're going to add filler alloys, are minimal castings, so they will exactly form the same macrostructures as a casting. I trust you enjoyed that module, and I hope it's built on the previous modules. Here's some further reading. Thank you very much.